Hello everyone, so we're continuing the conversation on pHs of buffer solutions and how to calculate them. In this example, we're told that a technical handbook states that to prepare a particular buffer solution, you should mix 63 milliliter of a 0.2 molar acetic acid solution with 37 milliliter of a 0.2 sodium acetate solution. We need to determine the pH of this buffer solution given the Ka, which of course is the Ka of the acid, because that's what the Ka value is. So we need to determine the pH of this buffer solution. Now, I want to do something a bit different here. So I'm going to do two things. So the first thing is we're given two solutions which we then mix together to form, of course, a buffer, because first we must recognize that, as usual, we have an acid and then its conjugate base. And if we mix those two things together, we will have acid mixed with its conjugate base in significant amounts. Hence, we should have a buffer solution. And so the thing that we can use is the Henderson-Hasselbalch equation. And to use the Henderson-Hasselbalch equation, we need the pKa, in other words, we need the Ka of the acid, and we also need the base and the acid concentrations in the new solution. But hopefully you recognize that we're mixing two different volumes here, and so those two different volumes will imply that we have a solution that has a final total volume. So V total is equal to, what's that, 37.0 milliliter plus 63.0 milliliter is equal to 100.0 milliliter. All right, so that is what is important to notice here, is that we're mixing two substances. Well, of course, yes, they don't react, but they're in a new volume. So our first important thing is then to determine the number of moles so that we can determine their new concentrations. So HC2H3O2, of course, is going to be equal to the concentration multiplied by the volume of that. And the concentration for the acid is 0.200 molar, which is mole per liter, multiplied by 63 milliliters, so that's 63.0 times 10 to the negative 3 liter, which gives me 0.0126 mole HC2H3O2. We can also calculate the sodium acetate solution, or the number of moles of the sodium acetate. That is, of course, 0.200 molar, and it's 37.0 times 10 to the negative 3 liter, and that is equal to 7.4 times 10 to the negative 3 mole sodium acetate. All right, so now we have the new, or the number of moles of each of these. They of course will have a new concentration because they're in a new volume. So you can go ahead and calculate their new concentration. So then, okay, so this is 0.0126 mole, and of course 100 milliliter, which is then liter, and 7.4 times 10 to the negative 3. Oops. In also 100 times 10 to the negative 3 liter. And this gives me 0.126 molar, and this 0.074 molar. Alright, so then we can use the Henderson-Hasselbalch equation, which is pH is equal to pKa plus log concentration of base divided by concentration acid. And in our case, in other words, this is always negative. The pKa is negative log of Ka plus log of, so the base in our case is obviously the sodium acetate. So that's the concentration of the sodium acetate. And the acid is, of course, the acetic acid. So that's HC2, H3O2. So we're given the Ka, so that's minus log of 1.8 times 10 to the negative 5 plus log of these values that we just calculated. So this one is 0.074 and this one is 0.126. And we can actually round, so the number that you get here, two decimal places for the two significant figures, 4.51. Alright, and that makes sense. It's an acidic buffer. It's not a strong buffer, strong acid, and if we check, the acid is in excess, an excess amount to the base, so it should be a bit more. All right, so that's how we do it. Now I want you to do just an interesting check for yourself. Calculate this again, but use the number of mole. So say log Ka and just say log of the number of mole of NaC2H3O2 and number of mole of HC2H3O2. In other words, my negative log of 1.8 times 10 to the negative 5 plus log of C3H was 0.0126 and this was 7.4 times 10 to the negative 3. 7.4 times 10 to the negative 3. You should see that you get exactly the same value. And hopefully it's quite clear as to why. So if we think about what is the Henderson-Hasselbalch equation a little bit. So it's pH equals to pKa plus log of a concentration of a base divided by a concentration of an acid, right? But what are these concentrations in? So meaning the concentration of the base is equal to the number of mole of the base divided by the volume of the, let's call it volume of the buffer. And the concentration of the acid is equal to the number of mole of the acid divided by the volume of the buffer, right? Same volume, because both this acid and this base is in the same volume, as we just did there, right? They're in the same total volume, but we divided them both by 100 milliliter. So they're in the same volume. They have to exist in the same volume. It's not like they exist in two different beakers. They're in the same beaker, same volume. So if you take then the ratio, right? So base divided by acid. And you put in what I just wrote here. So in other words, you have, let's call it N base divided by volume buffer, which is then, and then N acid divided by volume buffer. You should see that that then just gives you N base divided by volume buffer multiplied by volume buffer over number of moles of acid. And what cancels? That means the volume buffer cancels. And that's why the concentration ratio, the ratio of the concentrations, is equal to the ratio of the number of mole. And that's why whether or not you use the concentrations to calculate the pH or the number of mole, it gave you the same answer, because they're in the same volume. And that's why changing the volume of a buffer does not affect the pH. It just affects the capacity of the buffer. It doesn't affect the pH of the buffer. You're just diluting the buffer. You're just affecting its capacity, right? Because that ratio of amount of base to amount of acid, you're not changing that. So you're not affecting the pH. And it's just an interesting observation. So if you wanted to, you didn't have to calculate the concentrations. You just needed the number of mole of these two species. And because you know they're in the same volume, then you could have just gone ahead and calculated it directly. All right. So I wanted to take the opportunity to show this. In general, I'll use the concentration just to be consistent with our usage and whatnot. But if you want to be smart about it and do something else, this is one way. You can use the number of mole. All right, but you need to be explicit as to why. So that would be a good way of doing it. All right, cool. So thank you for watching, and I'll see you in the next video.